Argument and Lurk in 2025. Where are we so far? What are we doing with this company that has very nice Hornet-themed t-shirts? We're looking at what proving is actually looking like today, right? And proving today is a bit of an ISA fest. So this day, company after company after company since 2023 has latched on the idea that, hey, you know what, there's those instruction set architectures that are everywhere, and I have project after project after project that has figured out that VMs are really cool. ZK VMs are really cool, and especially the ones that have a generic instruction set architecture. They can take something that looks remotely like a CPU, and the idea is you're going to take your code, compile it to that instruction set architecture, and then you're going to have a proof, and it's great, and it's done, right? And to interpret this, you have to compare it to what you have before this. That is, before this, you had two models, right? You had the ISA model, and then the compilation to a circuit model. So the compilation to a circuit model, we all know, it's the circum model, right? The circum model is you write circum code and it compiles to a circum circuit. Nice thing, you get performance. Not so nice thing, it's a kind of a bitch to write a correct circum program, to excuse my French. Then VM is a lot more intuitive. It gets you back the intuition you have as a programmer. If you are running a loop, you don't care that it is provable that you will run 50 times through this loop and not 51 times. If your loop is early stopping, you only pay for the iterations that you actually ran. If you are doing branching, if you are an if, you're not paying for the complexity of both branches of your if, but only the if branch that you use, right? That's why we all like VMs. But there's one subtlety, which is this TCB acronym that is in my slide here, which is Trusted Computing Base. The Trusted Computing Base is basically what is the amount of code that needs to be correct for my prover to be correct, for my proof protocol to be correct. So Bob and Charlie are playing a game of ZK Battleship. What do I need as safe code to make sure that this game of ZK Battleship runs correctly? And the compiler is in there, right? That is, your ZK VM must be bug-free in order for the proof to hold and really prove what you intended to prove. But the compiler must also be bug-free for the protocol to prove that the ZK Battleship program you agreed to in Rust, in that high-level language, matches the thing that you're actually proving, which is the RISC-V ASA. So if you retain absolutely nothing else from this talk, you might want to retain that. We have a lot of data on compiler bugs. Compilers such as GCC and LLVM have been studied for decades. We have decades of back data on their bugs. And we have very nice researchers that have been pointing out and sorting by hand which bugs are optimization bugs and which bugs are, I don't know, the UX or the command line interface option number 42 being incorrect. And sorting that manually, they have gotten results. You have all the details in our blog post of us. There are several publications that all agree on that topic, which is that on average, on each of GCC or LLVM, you get 6 new misoptimization bugs. And those misoptimization bugs are chosen very specifically because they look like something that the compiler is doing post-compilation, where the compiler is, in that bug, violating the semantics of the code you've given it. So you give it a function to compute, and you're saying, here's the source code to a function that computes f of x equals 4 minus x. And the compiler compiles that to a function that computes f of x equals 4. That's an example of a misoptimization bug. What the compiler was trying to do is honestly simplify some of the intermediate variables in your function. It was trying to remove a lot of the boilerplate code, and it messed up. There are 6 new such bugs every month. Those bugs, on average, live 12 months. The numbers are eerily similar between GCC and LLVM. So 6 times 12 months, on every single release, every single commit number of GCC or LLVM, there are 72 misoptimization bugs that are documented reference on a confirmed issue on GitHub. Not to mention the one that might not be referenced, right? So do with that what you will. Those are just the facts that we have today. But notice that if you are betting $10 on a game of ZK Battleship, well, Alice is probably not going to give you precisely that program that they know is going to miscompile. But if you are playing a game of give me 1 million on my financial protocol, well, beware of what Alice might give you. Are you auditing the assembly, the RISC-V assembly? Because you really should. There's other options and more talking about this. I'm going to stop talking about this. But one last point I'm going to make is every time you have a compiler that compiles to a ZK proof, notice that a compiler bug is usually something we catch with unit tests, right? You get a compile function that computes f of x equals 4, right? You run it through 9. You're intending to get 4 minus x. You're supposed to get minus 5. You're going to get 4. You're going to think, oh shit, that 4 is not the correct result. Here's the problem with a ZK proof. You're hiding the inputs. You're trying to compute if the torpedo hits with respect to the position of your battleship, which you are absolutely not revealing at any point in the process. That's the entire point of playing ZK Battleship, right? You're hiding the inputs, and so the only thing you see is proofs that passed successfully. The ship were not hit, the torpedoes do not hit. And then your torpedoes have eventually covered the entire grid, and still you have not hit the ships. And the proofs are like, yeah, cool. There's no problem in your RISC-V ZK VM. I am not dissing RISC-V ZK VMs. This is not against VMs of any kind. This is just how compilers work today and the engineering data we have on what GCC and LLVM do. Okay, so there's a third model. The third model is called an abstract machine. We're going to go into what an abstract machine does, but here's why you should care. The productivity is as high as your high-level language if you favor the same language. The advantage and disadvantage is that this is language-specific. So I'm taking a high-level language. I'm taking your OCaml, your Haskell, your JavaScript, and I'm doing something that interprets that JavaScript directly. I am not compiling it to anything. I am using a machine that does not have any representation in hardware. So I'm skipping all of the steps that are there to model the hardware. My machine is resolutely abstract, it is minimalistic, and it has a single goal, which is to create a value out of the program and the arguments you gave. And it was designed in order to give semantics for a programming language on a whiteboard. Here's the use case for defining abstract machines in academia. Dear professor comes with a new programming language. They throw some syntax at the board, and then they wait. And they're like, dear audience, of course you understand how to compile with, how to compute with that syntax, right? Right? It's intuitive, right? And the audience, after a while, explained to that academician, no, it is not intuitive. You are indeed going to have to give us an idea of how that works. To which the academic was like, can I give you an implementation? I'm like, dude, you're an academic. We don't want to review your code. Like, this is very clear between us. Your code is not a thing we want to see ever. So here's a piece of chalk. Explain to us the semantics of that language. And so they defined abstract machines. This started in 1964. The first professor that did that was P.J. Landin. There's a crap ton of languages that have been defined in exactly that way over time. The abstract machines are by definition minimalistic because the guy that was designing them had a piece of chalk, and that's it.